It's not bad. Once you're into it, I guess it's not just like. Oh, yeah. That makes sense. Thank you. Thank you. Or do you have any plans? Like one of my friends are staying at night. That's like before 2. Yeah. So. For what?
Okay. So we are going to continue and finish up with our resting membrane potential of our neurons. So remembering where we were, what we're starting with, so that we can start to understand the nervous system. We're starting out with understanding why our neurons are starting out at a resting membrane potential of -70 millivolts. Because as we'll see later on today, we're going to notice that there is a change from that -70 millivolts. So a change in our membrane potential, changing from that resting state. We're going to start to see that we're going to have spikes of that membrane potential that trigger the release of our neurotransmitters, our brain chemicals, in order to make other neurons fire off. So we're starting out by figuring out how that baseline is created so that we can understand why it changes, how it changes, when it changes. Okay, so we had talked a bit about the sodium potassium pump. We talked about the equilibrium potential of sodium and potassium, how that relates to our membrane potential, our resting membrane potential being -70 millivolts. We looked a little bit at the permeability of that membrane. Now, permeability, very permeable to potassium. So potassium has more leak channels. That's what those channels actually are. Many different types of channels, but leak channels for potassium are about 25 times more common than our leak channels for sodium. So we can see all of that kind of going on in this picture. Okay. Know that the resting membrane potential, therefore, is closer to the potassium equilibrium potential. We know that the equilibrium potential is essentially the number that that ion is trying to make that membrane potential be. Once we get to the equilibrium potential for an ion, that ion stops moving overall, because that's the point where its chemical driving force and its electrical driving force are equal in magnitude, opposite in direction. So our electrochemical driving force is 0. Okay. So we're not at equilibrium for an ion, electrochemical force is not 0. As we're farther away from the membrane potential, as the membrane potential is farther away from the equilibrium potential, that force is stronger. Okay. This is just a summary slide of the forces on potassium. All right, so potassium, our big picture here is that potassium wants to leave the cell because it wants to make that cell get to -94. This is because our chemical force pushing potassium out of the cell, drawing potassium out of the cell, is higher than that electrical force pulling it into the cell. Opposite situation going on with sodium. That chemical force is into the cell, and when we're at our resting membrane potential of -70, our electrical force is also into the cell. So we have a really strong force for sodium to move into the cell at that starting point. All right, so we're gonna do. I want you to make a prediction. You're just gonna like type a word or a term. So what I want you to do, think about that cell membrane. Think about what we could do to move that membrane potential. Membrane potential is the -70, away from the resting membrane potential. So what I'm saying is like, what could we change about the membrane to go from the rest point of -70 to say like -50 or something? What can we change about the structure of that membrane? Gary, this one's gonna make us a word cloud, so we'll see how it looks. Take another couple seconds. If you really have no guesses, you can write, I don't know. If that word gets really big, I'll know lots of people don't know. Compare and see what our outcome looks like here. Okay. Cool. All right, so we got a bunch of options. So what we can see is that our biggest ones here, I'm gonna say, are the concentration, the permeability, and the charge. Okay. So we're gonna think about our cell to think about these concepts. Okay. So we have our, so we have our cell. You know, it's at -70. Okay. We want to think about how we can make that number shift. Okay. So at the resting membrane potential, what we have happening is like we're at a steady state, right? We're not at the equilibrium potential for either potassium or for sodium, but through our leak channels, we've kind of stabled out the movement. It's happening at a constant rate. We have our sodium potassium pumping at a specific rate, kind of maintaining that number. Okay, but we are going to see that -70 number, our resting membrane potential, change as we move forward. Okay, so in order, concentration is biggest. So it is true. It's not exactly what's going to happen in our situation, but it is true that, yeah, if we change our concentration gradient across that membrane, right? So if we suddenly remove that concentration gradient for sodium, and sodium has equal concentrations on either side of the cell, we wouldn't have a chemical driving force for sodium. We'd only have an electrical driving force. So that force for sodium to move wouldn't be as strong, which might drop us down lower, closer to our potassium equilibrium potential. So if that sodium potassium pump stopped working, stopped maintaining those concentration gradients that are half of our electrochemical driving force, that would definitely shift our resting membrane potential. What we're going to see instead, actually, we'll address the charge one next because what I'm going to talk about is permeability. If we changed the charge inside the cell, like, yeah, the change in this value is by definition a change to the resting membrane potential. So if that changes to -60, -50, +30, right? Those charges, that different on the charge inside, right? We've moved away from the resting membrane potential. And if we change the distribution of those charged ions on either side of that membrane, that would also change this essentially electrical measurement of what we have on either side. Okay. However, what we're going to see happening when we start to talk about neurons and the action potential is that permeability shifting. Okay. So when we're looking at that number line, where we see our equilibrium potential for sodium at positive 60, okay, our equilibrium potential for potassium down at negative 94-ish, and our resting membrane potential of negative 70 millivolts. Okay. One of the things we noticed was this negative 70 is closer to negative 94. So we're closer to the equilibrium potential for potassium. Part of the reason for that is we have all those potassium leak channels. So we have 25 times more of those potassium channels, right? Than we have of our sodium channels. And we only have like, most of our drawings, oops. Okay. We only have one for the sodium versus a lot for the potassium. So the reason we're closer to that potassium equilibrium potential is because the membrane is more permeable to potassium. So more potassium can physically get through that membrane. Okay. So as we start to change the permeability of this membrane to different ions, we are also going to end up shifting away from that resting membrane potential. So first, what we are going to see in our action potential, so I'll just use that as our example, is we're going to see a bunch more sodium channels opening, right? This is going to be one of the first steps. So when the sodium channels open, I have a written question, but take a second to predict what's going to happen when we open a bunch of sodium channels. Hopefully what you're all answering in your heads right now, right, is we're going to have more sodium entering the cell, right? More sodium entering the cell because that's the direction the sodium wants to move, which means we're going to have more and more positives flowing in, making this membrane potential more and more positive. That's what we're going to start to see as a neuron begins to fire, essentially. Cool. Okay. So when we're at rest, we only have a little bit of leakage for that sodium. This has a really high force, so it really wants to move, but it can't because of that low permeability. Only a little bit is able to leak into the cell. When we are at rest, we have more permeability for that potassium. So there's a relatively low force on it. So the leak isn't that big, which is still why we call it a leak, but we're down closer to that equilibrium potential, which is part of why that low force, right? If we were way up in the positives, right? If we were positive 60, which is where sodium wants to be, we'd have a low force for sodium, a really high force for potassium because we're so far away from its equilibrium potential. Okay. So this is why we need the sodium pump, sodium potassium pump, to keep those concentrations going, keep those forces at their resting states, keep this moving until at rest. Okay, so what we're going to see as we move into our next set of slides, which is the action potential, we're going to be charting and trying to understand what happens over time. So over time, we're going to see a shift from this resting membrane potential. Okay. We're going to start to see a shift until we hit a threshold value. So we're going to start to see different movements of ions adding up together over time and space until we get to a threshold value about negative 55, at which point we have tons of sodium channels open. So some of our channels, rather than being leak channels that are just open all the time, respond to this electrical charge in the cell. So as you get to this threshold value, that opens a bunch of channels that have previously been closed. So sodium is going to flood into the cell, peaking us up to positive 30. So we're not going to get all the way to the equilibrium potential for sodium, but we are going to get a lot of the way there. And then they're going to start to close And we're going to start to see potassium next, having more channels opening. And as potassium rushes out of the cell, that pulls membrane potential back down. We actually overshoot the resting potential a little bit because we have that flood. And then eventually we stabilize back out to the resting membrane potential. So when we say that like neurons or nerves are just like kind of zapping each other, right? Like sometimes they draw electricity in cartoons for neurons. This is why. So that electricity is really trying to indicate to you these changes in membrane potential, which is electricity, kind of essentially. Okay. We'll talk about each of these phases in detail and how it happens, but that's where we're leading up to in our next couple chunks. Now, before we move into that, it's worth spending a little time looking at this diagram of a neuron, because we're going to be talking about signals getting sent down our neurons, right? So essentially from a start to an end, right? And we have signals coming in as well. So all these arrows are showing the flow essentially of charges. Right? So I put some definitions here next to our neuron. I want to make sure that we can find all these places on the diagram, because we're going to have different things happening in different parts of our neuron. We're going to have different types of channels present in different parts of our neuron. So last time we got a question if we were going to talk about atypical neurons. In this unit, we're really just focusing on a neuron that looks like this and this shape. There are lots of other neuronal shapes, but we're going to focus on the basic, I think, easiest to understand one, so that we just understand the idea of the action potential and this flow of charges. Let's run through this. Make sure we're all kind of understanding what we're looking at here as we start to think about our neurons. Okay. So first we're going to talk about the soma. Okay. So the soma, whenever you see the word soma or the root S-O-M, this is a word that refers to the body. So like the bulk of the body. So if you see something referred to as like somatic, it's going to be talking about visible parts of like your physical body. When we're talking about a neuron, the soma, the body of the cell, is the part where we have our typical cell structures, our organelles, and our nucleus. So our body of the cell, our soma, here we see a nucleus in purple. So our little organelles, right, like our mitochondria, our endoplasmic reticulum, our Golgi, right? All of these would be here in the soma. So this part in the center, this kind of star shape, that's our soma. Next on this list, we have our dendrites. Now, our dendrites are primarily going to be concerned with communicating with other neurons and specifically with receiving signals. Okay. So our dendrites, whenever you see the root like dendro, that means like tree. Slightly less helpful when we're looking at this picture, but like our tree branches be like these things here. That's where that's getting its name. So here you can see the arrow of an incoming signal flowing in from these first little branches, then into the soma, where we'd be kind of collecting and adding up these signals that we're getting from other neurons. So think like a bunch of neurons wired together in the brain, right? We're getting signals from like neuron 1 over here, neuron 2, maybe signaling to these dendrites, a third neuron signaling over here, something like that. So all of these things I've structured here, circled here, sorry, are dendrites. Let's skip axon hillock for a second. We're going to talk about the axon and the axon terminals first. Actually, let's talk about the axon terminals first, because that's the one that from normal English you should be able to guess best from this list. Okay. So our axon terminals, terminal like the end, right? So our terminals, our axon terminals are here. Okay. So here at the opposite end of this neuron from our soma and our dendrites, we can see these little sort of finger-like structures. Our axon terminals, so you can see that they're like kind of buttony swellings here. This is where we're going to be releasing neurotransmitters. So we're going to send out chemical signals from these axon terminals. It'll take us a while to get there in lecture, but that's where we're leading, right? And then these chemical signals are likely going to pair up with another neuron. So you would expect to see, for example, some dendrites here on another neuron receiving those signals, and then the same sort of structure continuing. We're going to see neurons in a chain. We're going to have what we call a synapse between these axon terminals, one neuron, and then either the body, soma, or the dendrites of our following. That's how we see these connections forming. So that leaves us with the axon and axon hillock. Okay. So for the axon, I'll do that first. So the axon is the main place we're going to be thinking about sending the signal down our neuron, so down a string, down a nerve. And so that's the long, skinny part here. So as we start to talk about the action potential, it's happening here. So that's our axon. Axon is here. The axon hillock is probably the most subtle of these structures. And so the axon hillock is referring to this little pinching off bit as we lead into the axon. So I'm going to draw like a triangle here. Right, so instead of leading and connecting that soma to a dendrite, we have a swelling that's leading us into the axon. Okay. And this structure is going to be important for the initiation, for the beginning of that action potential. So that axon hillock, like a little hill, we're thinking of this kind of triangle pinching off point as a hill. Okay. This is where we're going to either fire off an action potential or stay at rest and not fire off an action potential. So we're going to be thinking next about how charges add together and what that means for our neuron, like what that's going to do overall for us. And this is really the point at which we are most interested in charges adding up together, because this is at the beginning of our axon. And if we hit our threshold value, we're going to send off an action potential, this racing change of charges down this portion of the cell. If we don't hit our threshold value, nothing's going to happen. We're not going to send off a signal. So we'll come back to this a little later as we start to talk about how neurons are talking to each other. But keep this in mind as we begin to talk about these charges and how we start that action potential. This is our kind of environment this is happening in. So these questions were mostly summarized in that in that little word cloud that we did, but I'm gonna leave them here for you for a second and read them just to make sure that you can answer these questions after we're done with today. These would be good things to make sure you can explain to yourself. Okay, so we're going to be talking about changes to our memory potential. One of these changes we'll see is something called a depolarization. Okay. What causes a depolarization is when we have sodium channels opening in response to a neurotransmitter binding onto them. Okay. That's the first way we start to have a depolarization. Our sodium channels open. I'm not going to answer these for you right now, but I want you to be able to answer for yourselves by the end of today. You want to make sure that you can understand or guess what change this would cause to the memory potential. So if we have a neurotransmitter, this chemical binding onto a sodium channel and opening it up, what's going to happen to that charge inside the cell? The other thing that we want to be able to understand is what if instead we have a neurotransmitter that tells our potassium channels to open? So it binds onto a potassium channel and an additional potassium channel opens. At this point, we should be able to predict what happens under each of these situations. Go over this right now. We're going to move into our action plan. For action potential, what we're talking about is how our neurons are going to convey a signal down the length of that cell and then talk to the next neuron in a chain or talk to a muscle, actually. So action potentials can also run down a neuron, and that neuron links up to a muscle cell telling it to contract. That's another thing that we'll see. So there are various things we have to understand first in order to actually fire off that action potential. So here are objectives for that. We'll walk through them one by one. So we're going to start by thinking about something called a graded potential. Okay. So graded potential can be a little potential. So we have that chart of the different types of potentials, the different words that include the word potential a little while ago. But when you see the word potential, right, we want to remember that a membrane potential, abbreviated with that VM, measured in millivolts, MV. Right, what a potential is when you're measuring the charge inside the cell versus outside the cell. Okay, so if we stuck an electrode, right, like a little 10 electric sensor thing here, right, and measured the difference of all those charges adding up inside the cell versus all those charges adding up outside the cell, that is what would give us a membrane potential, that difference in charge. Okay. So whenever you see the word potential, what it's talking about is some kind of charge related thing. Okay. So for our graded potential, this is going to be a small tune in our membrane potential, and it's often going to be really local. Okay, so we're going to see that actually, when I write that the cell is at -70, we can have small shifts to that, right? Like, so say we can go to -60, right? We can even have slight differences in charge in different parts of the cell. So if our whole cell is -70, maybe right here, we're at -72, and right here, we're at -68, things like that. So really, really tiny locations might not all be identically at -70 under certain circumstances. So this is what's happening with our graded potential. We're going to have a small change in the membrane potential. So like this shift right here on this little section of membrane to -68. That would probably be a graded potential. So we had a slight change right here in this little location. Okay. And our graded potentials, small changes, they're going to communicate over short distances. They're never going to race down that long axon and talk to another cell. Okay. All they're really going to be able to do is to change a little bit of the charge in their direct neighbors. So like the little bit of membrane that's right next to that patch, if we think about it. This is different than our action potential, right? So making this look more like a neuron, right? I'm drawing the axon hillock now, and then our long skinny axon leaving our page here. Our action potential is really large, and it's going to be able to communicate over long distances because we're going to see it racing all the way down that long skinny axon. So when we end up with an action potential, it's going to happen in a specific pattern. It's going to flow all the way down our cell. Okay, so if we're looking at these pictures, I'm in the center. So one of these pictures is showing us just some graded potentials. One of these pictures is showing us a couple of graded potentials and then an action potential. Second, to predict which is which. Show you what we're looking at. Figured out how to make image questions yet, but I will for next time. I talk through the answer. I'm going to tell you what's going on with these little pink arrows. So you want to think of each of these little pink arrows as a stimulus. So that's our formal term, a stimulus. But what's going on with these little pink arrows is you can think about it as like something has poked our cell, something poked our neuron. When I say poke, I mean it emitted a neurotransmitter that bound to some channels. Right, but you're thinking about another neuron just like saying, hey, do something. Right? So that's what's up with those pink arrows. We're trying to find our graded potentials. Graded potentials are each of these little bumps. So here we see one graded potential. Here we see another graded potential. And even this little dip counts as a graded potential, right? So anytime we see one of these little small changes, that's a graded potential. You can notice that each of those graded potentials in this diagram is happening in response to a stimulus, right? So we've had some kind of signal come into our cell, and it's caused that graded potential each time, right? So we had a signal come in, and then something happened in response in our membrane potential. And figure B, we do have an action potential. So the big potential, the big change, this is our action potential. That's the action potential. What we see happening here, this is looking at our membrane potential over time. So I'm going to go ahead and number these little stimuli. Okay. So this first stimulus, just like in our figure A created one little graded potential. Okay. Then we drop back down to our resting membrane potential of -70. So we could draw a number here. We know that our rest point is -70. These second signals, these next two stimuli, 2 and 3, they came really close together. Okay, so for stimulus 2, we started to make a little second graded potential, right? Which on our first figure, we even give them the same numbers. So in figure A, we had time for that graded potential to go up. And then our sodium potassium pump is still working. We're stabilizing the membrane potential. So we fell back down to rest, okay? However, what happens here in this figure B is that before we have time to do the second half, this falling back to rest, right? We got to this peak. Stimulus 3 came in. So the stimulus 3 came in. It would have caused its own graded potential. In this case, a positive one, so like it would have been another lump, not this dip from PJ. Okay. And so they start to add up, right? So we didn't have that membrane potential go back to rest. We didn't have enough time. And so we add on that little change that's happening in response to stimulus 3. And this is where we hit this threshold value. This is that threshold of -55. Call it the threshold potential. Threshold. I think that's too many H's. Sorry, y'all. Okay. Threshold potential. Okay. So once we hit -55, that's high enough that something special happens. And the special thing is that we fire off this action potential, which is always going to spike up to +30. Right. So when you're thinking about numbers to know in terms of our nerves and our neurons, you do want to know that -70 is our resting membrane potential. You're going to want to know that -55 is that threshold value. You're going to want to know that the peak of the action potential is +30. And it's helpful to also know the values of those equilibrium potentials for sodium and potassium. Okay, so potassium was -94. And sodium is +60. Okay, and we'll keep talking about these as we go through all the neuron stuff, but knowing those numbers is really going to help you figure out what's going on. Those are graded potentials, you know. Okay. Go ahead and answer this question. Trying to see if that's coming in over time. Top one is the main thing we've been talking about so far. So I'm glad that we all recognize this is true, right? So we have a strong electrochemical driving force for sodium to move into the cell. That is true. But actually all the rest of these options are true as well, right? So we mentioned, right, that permeability of that membrane, right, makes a difference for sodium. So at our resting membrane potential, we don't have very many channels for sodium open. So not much sodium can move, versus potassium can move pretty easy because we have 25 times more channels open for potassium. So at rest, our membrane is way less permeable to potassium. Okay. We also, well, that's also directly related to this fewer channel split, right? So sodium is experiencing that lower permeability of the membrane because it has fewer channels. And that's also tied to this third thing, right? So we have a slow leak for sodium because the membrane has low permeability to sodium because there are fewer channels open. So all of this is actually factually true. Have a Q&A slide up, but can you guys still type questions on your side? So take a second, and if you have questions, this is like those in, I'll take a look at them here. Again, I'll keep checking. Let's see any at this time. Okay. Looking at where these graded potentials are happening, going to help us think about how we get to the action potential running down that axis. Each graded potential is going to be initiated by a stimulus. That was those pink arrows. So we have pink arrows, stimuli again on this figure at the top. X, one stimulus. Then we have a stronger stimulus listed as stronger X. Okay. Each of these stimuli is going to create a small change in the membrane potential, originating at the location of that stimulus. So basically, the cell is going to start to change the membrane potential at that location where it gets poked. So the stimulus is coming in a physical spot. Okay, so here we might think about the stimulus as being on the soma of the neuron, so that body part. Maybe these points are dendrites, so you might have a stimulus poking in here on a dendrite, creating a graded potential originating there. So these are small local changes to the graded potential. We call them graded potentials because they're not all the same. When we talk about action potentials, every time you see a graph of the action potential, it's going to have exactly the same numbers on it. It's always going to peak up to positive 30, always going to drop down below rest, always going to come back to rest. Always starts by hitting that threshold of negative 55. So every single time you see an action potential, it looks exactly the same. But graded potentials are not like that. You can have a small graded potential or a big graded potential. You can't have a small action potential or a big action potential. That doesn't make sense because it can't go higher than positive 30. It's not going to go lower than positive 30. It's always identical. Right, so that's why I use the word graded. So graded is referring to like a scale, like degrees. So that is because we can have this difference in magnitude, right? So we have a small one here, we have a bigger one here. That's that graded part. The other place we see a grade So you can see kind of a high-low gradient happening here in the cell. Right, so the change to that voltage, the change to the membrane potential, going to be a big change where the stimulus came in. And then it's going to get smaller and smaller and smaller as we move farther away from that original location. So this is just like when we look at our chemical gradients, right? We're going from a high to a low conceptually, okay? As we change spatially our location. So that's how that magnitude and the word graded are related here for the graded. They're spread by electroatomic conduction. Basically, we're just saying they're spread by changes in the ion levels. Essentially, that's good enough for our understanding of that concept. But we do want to know that they decay in strength as they move away from that original spot. So they're decremental, they're decaying. That change in charge is getting smaller depending on where we record it. So if we record here near the stimulus, we see a bigger change to the membrane potential than if we record it here at the axis. So it's going to decrease as we move. Yes, this is where we will pick up next time. I recommend taking a little look, if you haven't yet, in the section in your book, starting out the action potential. We're going to start with spatial and spectral elevation of these graded potentials. Once you get it, it really makes sense, but sometimes it takes a second to get it. So try to preview that. When I say it, it's not the first time you have to